Hello everyone, my name is Jan Jančar and I'm a PhD student from the Center for Research on Cryptography and Security at Masaryk University in Brno in Czech Republic. And I'm presenting work done with all of these great people from Max Planck Institute for Security and Piracy, from IRISA, and also from the George Washington University. This work was also presented at IEEE SMP 2022. If you want more details on the paper, supplementary materials, go and check out this link or scan the QR code. And now this work is all about what cryptographic library developers think about timing attacks. So let's jump right in and go on with timing attacks. Timing attacks have been around for a while. They are now more than 25 years old, introduced in this 1996 paper. They're now even older than me. And so what happens in a timing attack is that the duration of an operation leaks some information about secrets that are used within this operation. For that operation, you can imagine any sort of usually cryptographic operation like ECDSA signing or some RSA signatures or things like that, or AES encryption and so on. And if the duration of an operation somehow depends on secret-derived values, the attacker that can measure the duration can extract information on these secrets. Well, why this happens is mostly due to branches or memory accesses based on these secret-derived values. So you would have a condition on a secret key bit in code, or you would have memory access based on some secret-derived values, like in a table-based AES implementation, or you would have some sort of a conditional jump, like in scalar multiplication in elliptic cryptography. You would do a jump based on a key bit. But not only due to these two things that the attacker can measure, but also due to sometimes variable time instructions. So certain architectures have instructions that take variable time depending on the data they are provided with. And now very recently it was also been shown that the frequency scaling, basically the way the CPU that is executing instructions, how it changes its frequency based on some patterns in the data that are fed to its instructions, that can also leak information on secrets because it changes the overall duration of some operation which the attacker can measure. Now what's interesting for us, or for me specifically, about timing attacks is that they are still around. With these recent examples, some from 2020, a group of vulnerabilities in ECDSA signing, in a smart card, and several open source cryptographic libraries, and in 2022, the Harsbit vulnerability, which shown that this frequency scaling leakage is also a thing that we need to worry about. Now, luckily, there's this thing called the constant time code practice, where you can try and structure your code in such a way that you avoid these things that leak, right? You avoid branches or memory accesses based on secret-derived values. You avoid these well-known sort of variable time instructions, and we don't deal with frequency leaks at this moment. But let's just avoid these main things. This is an example of such a constant time code example. Taken from the BinSec-REL paper, so a paper from about a tool for verifying constant timeness. And this example it's a constant time select, right? So you have two 32-bit unsigned integers, and you want to select and one selection bit, and you want to select based on that bit a particular integer, and you want to do it constant time because this bit might be a secret derived value. Now this code looks nice and sort of constant time. There are no branches, and there's no obvious branches in this code, and also there are no obvious there are no memory accesses based on secret derived values. So we should be fine, right? If you compile this with the latest Clang and you turn off optimizations, so you say optimizations to 0, you get no conditional jumps. The code is all right. Nothing bad happens. However, if you compile this with optimizations turned on, with a recent Clang for this architecture, Clang inserts a conditional jump and therefore leaks the value of this bit. If you want to experience this yourself, scan this QR code. There's a link there to the Godbolt compiler explorer, where you will see this code compiled with these two configurations, and you will see that one contains a jump based on this bit. This is because the compiler is sort of intelligent and optimizes this and notices that what you're trying to do is just select one or the other integer, and well, obviously this jump is apparently faster. So what this means is that we have to verify constant timeness. We cannot just rely on this code practice, because code that looks constant time might not end up being constant time. Luckily, there are these tools for verification of constant timeness, which can do just that, right? They verify at some level some property related to constant timeness, related to the absence of timing leaks. Now, they work on very different targets. Some target the C or the source level. There is one tool that's for Java, so that's the source there. Or they target some intermediate representation, something like LVMIR, but I bundled both of these together. And what these have in common is that the analysis at the source level or at the IR level is really nice. You have all the information there. However, you have this issue that I've just shown you, right? Where you have a code that's supposedly constant time, has no branches on secret derived values, there's no memory accesses, no sort of variable time instructions visible. You don't have instructions at this point, you just have the C code, right? But then with the compiler selection, you actually get a leaking binary. So if this analysis happens at the C or sort of IR level, this is still above where the optimizations could happen that turn this constant time looking code into non-constant time binary. There are also other tools that have a domain-specific language. In this case, it's the fact tool, which basically you write code in this domain-specific language, you annotate it somehow about what are your secrets, and then there is a const transformation that turns this into constant time code and then into constant time binary. However, in that case, you have to rewrite your cryptographic code in this specific language. And there are also other tools for the sort of generating constant time implementation of crypto, but they often sort of go from this domain-specific languages. And also there are tools that work on the binary level, right? So these, you give them a binary and they somehow argue whether it's constant time or not. Perhaps this binary must have been created through some specific process, but that really depends on the tool. And these tools use very different techniques, right? So quite a large part of these tools use techniques from formal methods like symbolic execution and so on, really like formal methods, and then they provide sort of strong guarantees. Well, if they finish and if the result is not unknown, they tend to provide strong guarantees on the result, like whether there is leakage or whether there is not. Then there are dynamic tools, which usually run the code with some instrumentation, and then they observe the results of that instrumentation, if there were any conditional jumps, if there were any memory accesses, and so on. And finally, there are tools based on statistics, which basically run the tool with many different inputs and time it as an attacker would, and see statistically if there are any sort of observable leaks. You can find all of these tools and more in the future, hopefully tutorials and guides, installation scripts on behind this QR code and on this link, where we will try to sort of get this info on these tools and make these tools as usable as possible. So I've just explained how we have this constant time code practice, and even if that's not enough in presence of these nefarious optimizing compilers, we have these tools for verification of constant timeness. So timing attacks shouldn't really be a thing, right? So why are timing attacks still around? Is it that timing attacks are just not part of threat models of cryptographic libraries? Is it that the library developers do not know how to protect against timing attacks? Is that the developers are unaware of these tools that could help them? Or in general, why are the tools not being used effectively? And these are the questions that, let's just ask cryptographic library developers. They are the ones that will know answers to these questions, because they are the ones that would fix these timing leaks. They are the ones that would use these tools for verifying resistance of code against timing attacks. And this sounds like a great idea, and it's exactly what we did. So we decided to run a survey targeting open source cryptographic libraries and their developers. We focused on the most active contributors using the number of comments. In the end, we invited more than 200 developers from 36 libraries, and we got 44 valid responses from 27 libraries. For the rest of this talk, I will denote the participants with this person symbol and the libraries participating with this book symbol. And I must say that this participation rate is really great, and we are really thankful for our participants because without them, these libraries wouldn't exist, and our research wouldn't exist as well. So we've got many popular libraries such as OpenSSL, LibreSSL, libgcrypt, even some Rust ones, or Amazon S2M. And from these libraries, we feel like we've got the developers that we wanted to ask. So we've got a lot of core developers, maintainers, committers. We've got the people that can make the decisions that influence how these libraries are developed and what their posture towards timing attacks is and if they get fixed and so on. In our survey, we first asked about the participant background, their background in cryptography, experience developing cryptographic code, and this academic/industry split. Next, we focused on the library and the participants' role in that library. So we asked them about their role, whether they are sort of this committer, developer, and so on, and then how the library makes design decisions, whether there is voting or whether there is some sort of a formal process. Next, we focused on the library's threat model with respect to sidechain attacks, specifically asking about timing attacks. Then we asked about timing attack protections in the library, whether there are any, and if so, which, and how were they introduced. And finally, we asked about whether there is any testing of timing attack resistance in the library, and if so, how that is done and how often. Then we focused on the tools and participants' awareness of these tools for verifying resistance of code against timing attacks. Then we asked about how did they learn about them, if they knew about some of these tools. And we also asked them about experience using these tools to sort of tell us how they use these tools. But we suspected that a large part of our participants wouldn't have experience using these tools or would not even know these tools, but we still wanted to get their opinion. So we presented them with properties of 3 distinct groups of tools. These groups were dynamic instrumentation-based, statistical runtime tests, and formal analysis tools. And the properties we showed them were basically the requirements of the code that the tools need to run, and also the guarantees on the results that the tool give you. And these groups of tools are very different in these aspects, in these properties, where formal analysis tools give you great guarantees, but also require kind of lots of annotations on your code. Sometimes even require things like proving loop bounds or sort of have various limitations on what they can run. Whereas, for example, statistical runtime tests have very little limitations, but also the guarantees they give you are quite weak, are statistical, and might just not catch some leaks that are way too small, but still might be exploitable. Then we asked our participants about likeliness of use of these 3 groups of tools and their reasoning behind them, basically hypothetically whether they were likely to use these tools. And finally, we asked our participants about general thoughts on timing attacks and on our survey. And I must say that most participants liked our survey and wanted to get involved more in the sort of research and in timing attacks, which made us really happy. Now let's get into the results. Luckily, we found out that developers know about timing attacks. 100% of our sample knew about timing attacks, though their opinions varied. Starting from this one quote that ended up being in the title of our paper, that timing attacks are not that hard to mitigate, at least with the compilers this participant is using right now. Now I would like to know what these compilers are and to know more details about the process of this person. Sadly, that was not there. But there was this sort of spectrum of opinions ranging from this strict view on timing attacks that is totally obvious for everybody right from the start, that protections against timing attacks is necessary, to this more skeptical view that for many cases there aren't enough real-world attacks to justify spending time on preventing timing leaks. Now, however, these opinions varied. Most libraries considered timing attacks a threat in their threat model. So 23 libraries did include timing attacks in their threat model, and 2 did not include. However, these libraries often differentiated between local and remote attacks, with 20 including remote attacks and 16 including local. Specifically, they differentiated using wording like remote observation is obviously a bigger issue. They gave a larger priority to remote timing attacks, things that are exploitable over the network, and they gave less priority to sort of local attacks where you really need the cache access or very high precision timings. However, their reasoning for including these timing attacks, a threat in their threat model, varied, with some general that timing attacks are a relevant threat because they are, through some more specific, telling us about loss of reputation. For example, it is never fun to be a bug that a new research paper is talking about exploiting. And some argued that the target environment of the library is such that it's exposed to timing attacks and thus needs to be protected. Now, even though this most considered timing attacks a threat in their threat model, the claiming resistance about timing attacks, only 13 libraries claimed full resistance against timing attacks. But these 13 libraries are, let's say, quite confident in that, because for me, claiming full resistance against timing attacks in the current, let's say, knowledge about what timing attacks can do and how hard it is to protect all the possible for all the possible architectures and implementation configurations and so on, to be fully protected against timing attacks, it's a pretty bold claim. However, 10 libraries said that they are partially protected against timing attacks. This partially might, however, be sort of an issue from a user's perspective. If you're using a cryptographic library that's partially protected against timing attacks, how do you know which parts of that library are protected and which aren't? Such that if you want to use just the protected parts, how you go about that. Whether that's something that's documented, whether that's something that you can sort of enable, and what are the defaults, if it's enabled or disabled by default. Now, there was also this strong opinion showing that this is just how you write cryptographic code. Every other way is the wrong approach. The code should just be resistant against timing attack. I know, surprisingly, 3 libraries claimed no resistance against timing attacks. Now, these libraries shown various protection techniques, with most choosing what we call the constant time code practice, what I've described at the start, that conditional branches and lookups are avoided on secrets, and sort of with the addition of some more tricks like assembly code and common tricks, which are there to hope to prevent compiler optimizations. However, as the BinSec-rel paper has shown, and the tool has shown that, well, yes, these compilers are optimizing out there, and they are quite nefarious with that, and they will sometimes turn constant time looking code into non-constant time code, perhaps even with these common tricks. So 9 libraries reported using a constant time algorithm. Sometimes there is a well-known algorithm for something like scalar multiplication on a elliptic curve. There is the Montgomery ladder, which is a well-known constant time algorithm. And there are other various techniques reported, like blinding, slicing, assembly, or hardware features like ASNI. And one more protection technique that I would like to point out is our random delays, where one particular library expressed that they use random delays in their code as a countermeasure against timing attacks. And I must say that this is really not a good countermeasure. With enough samples, you can average out those random delays, or perhaps with local attacks on the cache, you really don't care about these random delays because you're attacking a different thing. So I suggest to anyone to go and try to find which library it is and perhaps get an attack or two on this library with this particular countermeasure. Now let's move on to the tools. Tools for verifying resistance of code against timing attacks and the developers' knowledge and views on those. What is nice is that 33 developers or participants heard of at least one tool. The most well-known tools were CTGrind, CTVerif, and MEMSAN. And CTGrind was so well-known so simple that some developers independently came up with the approach and we're using this CT-grind approach before the tool even existed. So to explain CT-grind is really a use case of WAL-grind, the tool, or let's say the memcheck component of WAL-grind, the tool, in which you sort of you mark areas of memory that you consider secret, you mark them uninitialized, and then what WAL-grind will do is that during execution, WAL-grind will trace how these uninitialized areas of memory affect other other derived values, right? And through this process of shadowing. And if you ever do a conditional jump or a memory access based on an uninitialized value, WAL-grind will tell you that you are doing so just as you do that. So you can use WAL-grind to warn you about conditional jumps and memory accesses based on uninitialized values. But if you mark your secrets uninitialized, then you can do so based on secret values. However, the most important result here and on this slide is that most of these tools were unknown, meaning that apart from these 3 that I've shown, out of the 25 that we asked about, only one more tool was known by 2 people, and the rest were known by 1 or 0 people. Now, it is really hard for a tool to be used or useful to these developers if it is completely unknown. No one will use a tool if they do not know about it. And that is somewhat reflected in this. In these results, where only 19 tried to use these tools out of the 33, but most reported that lack of time was the issue that they had with the tool. They just didn't have time, or there wasn't enough priority for them to use the tool to detect possible timing leaks. Other issues that were reported was the inability of the tool to ignore known issues. So let's say you have a known but sort of benign leakage in your code, and you want to just ignore that for the time moment because handling that would be too expensive, but you just want to sort of analyze these other parts of the code. So some tools cannot properly do that, and that was what the participants complained about. But also, it's hard to use a tool if it's not maintained. You know, where will it be in 5 years? Will it still run? Will it still sort of give valid results? And it's really, really hard to use a tool if it's just completely not available. Now, some of the participants are just outright unlikely to use some of the tools. When we asked the participants about their likeliness of use of these 3 groups of tools, the formal analysis tools, the statistical runtime tests, and the dynamic instrumentation tools, based on our description of what the tools need to run on the code, the requirements they have, and the sort of level of guarantees that they provide, we figured out that participants perceived formal analysis tools as way too much effort. As this one quote puts it, formal analysis tools are not really usable by mere mortals yet. Whereas for dynamic and statistical tools, participants saw them as an acceptable trade-off between effort and guarantees. So with that, we've identified this leaky pipeline of developers trying to use these tools to verify constant timeness of their code, with 44 developers entering and only 17 developers meaningfully using these tools to verify the constant timeness of their cryptographic code. And if we went further and looked at how many of these developers use this code in an automated manner, in CI/CD, in a sort of complete way for the whole aspects of the library, such that if there was a new issue that was introduced, it would be caught in time, we would get an even lower number, perhaps in the single digits. So what can we do about this? What can we fix? Well, the tool developers should make the tools more usable. The tools, first of all, need to be available somewhere. There need to be source code releases for these tools. It happens way too often that there is a paper about the tool that's published. It even gives a name to the tool, but then never releases source code for the tool. It just never ends up anywhere, and no one can ever use it. The tools needs to be, on top of that, needs to be easy to install. There needs to be documentation, examples, and things of that sort. Otherwise, the developers will not use these tools, and it's too much time and too confusing. The tools also need to be promoted at appropriate venues. So as we've seen, not many developers really know about all of the tools that are possible. Some tools that might fit their use case, so they need to be promoted where possible. The cryptographic library developers should use these tools ideally in an automated way, ideally included in CI, such that any changes in the code that introduce an issue are automatically detected and can be handled. Developers should also try to eliminate all timing leaks, no matter how small they might seem, as the attacks can get better, and a leak that might seem benign can get to be exploitable in just a few steps. And also developers should strive to mark secrets in code, because this is helpful for a lot of the tools that require this sort of annotation, but also for the users of the library to know what is secret and what is not. Now, compiler writers should add support for secret types, and then do not introduce these timing leaks, or do not perform optimizations that might introduce timing leaks based on these secret types. But in general, we think that asking for secret types is a sort of a big ask. But then the sort of first step towards that is to give more control to developers to stop introduction of timing leaks. So more control over the compiler and over some of its optimization parts at some point to make sure that code that really needs to be constant time stays constant time even as it's optimized or compiled. And finally, standardization bodies. So for example, NIST, in the case of the post-quantum competition, these standardization bodies should encourage submitters to use these tools to detect potential timing leaks in their code. And we feel like these standardization bodies should require constant time code just outright for all of their submissions, and not just sort of encourage submissions to be constant time. So we've asked cryptographic library developers what they think about timing attacks, and we've found out that they know and care about timing attacks, but they do not know most tools for verifying constant timeness, and they do not use these tools, mostly due to lack of time. We've identified this leaky pipeline of developers trying to use these tools for verifying constant timeness and failing at doing that. And we've also identified this preconceived notion of formal analysis being just way too much effort for not much gain. So that's it for me. Thank you for listening. If you want more information about the paper, you can scan this QR code, you can go to this link for supplementary materials, and you can also tweet at me.